Thanks to Brilliant for sponsoring today's video.
Today we're going to look at the famous long division puzzle written by none other than the Nobel Prize winning physicist Richard Feynman. This puzzle is actually in a letter that he wrote to his mother. Okay, so let's see what we have here. So we've got this kind of structure of a long division problem. So let's see, we are dividing a 3-digit number into a 7-digit number. And we're getting a 4-digit quotient. And this letter A represents, well, one of the digits. And A can be any number between 0 and 9. And then each of these dots can be any of those digits as well, except it cannot be equal to A. And before we get started, I'd like to point out that there are lots of solutions to this on the internet, and they all follow the same kind of structure. But maybe a good source to what our solution is fairly similar to is this post that I found on Quora. You could find that by Googling the following line. Okay, so let's maybe do a first step, which is fairly easy. So if we look at this chunk, we notice that the only way to subtract a 3-digit number and a 4-digit number and get a 3-digit number is for that 4-digit number to start with a 1. So that means that we can go ahead and put a 1 in that location. Okay, so that's good. But let's also notice that part of that subtraction involves an A minus A. But of course that's going to give us a 0 in the correct digit of the difference. Okay, so that's looking good. But now at this stage it'll be extremely useful to introduce some variables for the digits of the divisor and the quotient. And that puts us in a position to dive into really the meat of our solution.
Are you ready to unlock your full potential? Dive into the world of knowledge and ignite your intellect with Brilliant.org. Brilliant is a learning experience that's as engaging as it is effective. Brilliant offers interactive, hands-on courses designed to make you not just understand, but truly master concepts in math, science, computer science, and more. With Brilliant, learning becomes an adventure. From problem-solving puzzles, like the one in today's video, to real-world applications. Each course is crafted to empower you with the skills that you need to excel in today's fast-paced world. Whether you're a student, a professional looking to upskill, or just someone with a thirst for knowledge, Brilliant has something for everyone. Say goodbye to dull lectures and hello to the exciting journey of discovery. Unlock your potential with Brilliant. Join a community of curious minds and let the brilliance begin. Visit Brilliant today and take your first step towards a brighter, more knowledgeable future. Treat yourself this winter with a unique hands-on experience by going to brilliant.org/Penn for a 30-day free trial, and the first 200 people will get 20% off their annual subscription. Thanks once again to Brilliant for sponsoring today's video.
So let's recall exactly how the digits of the quotient align with the lines that we have in our long division problem. So if we take the first digit or the leading digit of the quotient and multiply it into the divisor, we should get this line right here in the long division problem. So we can write that as follows. So we have x, that's the leading digit of the quotient, times our number BAC, so it has digits B, A, and C, and we'll get a number of the following shape. So it'll have 2 unknown dots, and then it'll end with 2 A's. But then this second digit of the quotient will multiply into the divisor, and that should give us this line right here. So we could write that as y multiplied into BAC equals, well, 2 unknown dots, and then ending in an A. Now let's notice that we get something very, very quick about the size of x and y here. So here we're multiplying x into BAC and we're getting a 4-digit number. Here we're multiplying y into BAC and we're getting a 3-digit number. I guess I should point out here that we're not having any leading zeros. So what does that mean? Well, that means that x must be larger than y. So that's really good. We've got a condition on two of our unknowns already. So we've got that. X must be larger than y. And now our next step will be to take this BAC in both of those cases and then rewrite it in terms of, well, what we mean by that expansion. Okay, so let's take that and rewrite it in terms of the expansion. So we've got x times 100b plus 10a plus c equals, well, we don't know what the first bit is, so I'm just going to write this as 100 times, well, some certain number that we don't know, but I'll just write that as this pink box, and then it'll be plus, well, this is representing 10a because it's a in the tens place, and then we've got an a in the ones place. So putting that all together, that is 11 times a. Okay, so let's just note that here we have b in the hundreds place, that's why we have 100b, and capital A in the tens place, that's why we have 10a, and then c in the ones position, that's why we just have c. And now we'll do a similar expansion to this second line. So here we'll have y times, well, it's again going to be 100b plus 10a plus c equals, well, now it'll be 10 times something, because notice we need to eat up the second digit, the tens place, and the hundreds place. So I'll use 10 times some green box, which is unknown, plus our number a. Okay, great. And now we're going to use the language of modular arithmetic to simplify this a little bit. And, well, what does that really mean? Well, we're going to work mod 10. So working mod 10 means we're going to divide these equations by 10 and only look at the remainder, which is actually quite easy here because if we divide 100 by 10, that gives us a remainder of 0. 10 by 10 will also give us a remainder of 0. And then the right-hand side is similarly simple to reduce mod 10. Okay, so let's make that reduction. So let's say this magenta means that we're reducing this thing modulo 10. We're dividing by 10 and keeping the remainder. So now our first equation will be c times x is congruent to, well, we have 10a plus 1a. Well, that'll just become a, so it's congruent to a modulo 10. And then we have, from this second line, c times y is congruent to a modulo 10. Oh, but they're both congruent to a mod 10. That means they're congruent to each other mod 10. So let's put that in there. So this implies that cx is congruent to cy modulo 10. Oh, but that means that c times x minus y is congruent to 0 modulo 10. Just by doing, some simple arithmetic operations. Okay, well, what does that really mean? That means if we divide c times the quantity x minus y, we get a multiple of 10. But let's see. C is a number between 0 and 9. X minus y is also going to be between 0 and 9. So there are only a couple of, or actually exactly 4 multiples of 10 that you can arrive at by multiplying two one-digit numbers. Because this c is a one-digit number, and this x minus y is also a one-digit number. Okay, so what are those multiples of 10 that you can get at from that setup? Well, they are 10, 20, 30, and 40. So that means we have c times x minus y must come from the set 10, 20, 30, and 40. Okay, so now let's look at each of those individually and see what we get. Okay, so we just arrived at this set of possibilities. C times x minus y was from the set 10, 20, 30, or 40. Well, you might say, we're missing a multiple of 10 that we could have arrived at, and that is 0. But actually, it's impossible for c to be equal to 0. Because if c is equal to 0, recalling that c is right here in this multiplication, then that means that a is also equal to 0. But that contradicts this setup over here that each dot cannot be equal to a, because recall that c was one of those dots from before. So that leaves us with only the possibilities that c is, well, 10, 20, 30, or 40, like we previously discussed. And a similar thing holds for x and y. So those can also not be equal to 0. Okay, so now let's work at each of these individually. So let's look at the case first when c times x minus y equals 10. So let's color code it like this. We've got that blue underline to this blue box. So let's first note that c cannot be equal to 5. And that's because if c is equal to 5, well then that means a would be 0 or 5. Oh, but it can't be 5 because it can't be equal to c. But it can't be 0 because then lots of other things would be 0 as well. Okay, so let's point that out over here because that's going to be useful throughout. So c is not equal to 5 based off that discussion that we just had. Okay, great. So now if you're multiplying two numbers and getting 10, well the only way to do that is 2 times 5, but c cannot be equal to 5, so that means that c must be equal to 2, which means that x minus y must be equal to 5. So that gives us several possibilities. So we can have x is equal to 9 and y is equal to 4. That difference is obviously equal to 5. We could have x equals 8 and y equals 3. That's another one of our possibilities. We could have x equals 7, y equals 2. That's, again, another possibility. Or we could have x equals 6 and y equals 1. Oh, but actually y equals 1 is not allowed because if y is equal to 1 right here, then c and a are the same, which is again another contradiction from our rule over here. So let's maybe get rid of this possibility. This is not allowed. But all of the remaining possibilities are allowed. Okay, great. So maybe let's put a box around this because we have some possibilities that we will eventually need to test. Okay, so now let's move on to the next, main possibility for c times x minus y, which is c times x minus y equals 20. So again, c cannot be equal to 5, which means that c must be equal to 4, and thus x minus y must be equal to 5. Oh, but that's going to give us the same possibilities for x and y that we enumerated down here. So we've got x is equal to 9, y is equal to 4, x is 8, y is 3, and x is 7, and y is 2. And again, this last possibility is never allowed. So now let's move on to the next main possibility here, which is that x minus y times c is equal to 30. And let's see how this would go. So again, c cannot be equal to 5, so c has to be equal to 6, which means x minus y is equal to 5. So let's see, c is equal to 6, x minus y is equal to 5. But now let's see what we get from that. Okay, so our first possibility would be x is equal to 9, y is equal to 4. Oh, but if we go into that, let's notice we have a 4 here, and then we have a 6 in this digit. But if we have a 4 here and a 6 in this digit, then that will imply that a is also equal to 4, because 4 times 6 is 24. But that would make a and y the same, which is a contradiction. So let's maybe pull that out. That means that a is equal to 4, which again is a contradiction. Okay, so now moving on to the next possibility, which is x is equal to 8, y is equal to 3. But we can do a similar analysis here. So if x is equal to 8, and then c is equal to 6, well, 6 times 8 is 48, but that means that a is equal to 8 based off where the a is in this digit right here. So a is equal to 8, but then that's another contradiction because x and a are the same here. And then one last case, let's say that x could be equal to 7 and y could be equal to 2. But again, pushing this back here, if we've got a y equals 2 here and c is equal to 6, well, 6 times 2 is 12, which means a is equal to 2. But again, those two things are not allowed to be equal by our rule over here. Oh, but that exhausted all possibilities here. So actually, all of the possibilities were not possible, which means that c cannot be equal to 6. Or, in other words, this c times x minus y is not allowed to be 30. And then I guess we've got one more main possibility, and that would be, what if c times x minus y is equal to 40? And again, the only way for that to occur will be c is equal to 8 and x minus y is equal to 5. Again, because we need two one-digit numbers to multiply to get 40. But we'll see here that all of the possibilities associated to this are okay. So in other words, we could have x is equal to 9, y is equal to 4, and the other two possibilities as well. Okay, so now we've got all of these possibilities to test, so we've got a bit of work to do, but it shouldn't be too bad. Let's jump into it. So after all those calculations we just did, we came up with the following possibilities for c and xy, where recall that those represented the following digits in the quotient and the divisor. So we could have c equal to 2, 4, or 8, and then we could have the ordered pair xy equal to the ordered pair 9, 4, 8, 3, or 7, 2. Let's also recall that earlier we had the following equation. We had x times 100b plus 10a plus c equals 100 times something plus 11a. And that actually comes from this line right here. It's this leading digit of the quotient multiplying into the divisor, giving us this line. Just expand it out a little bit. Then if you reduce this mod 100, which is simply dividing by 100 and keeping the remainder, you'll get x times 10a plus c is congruent to 11a modulo 100. And now the game is to simply work through these cases one at a time. Observe that there are exactly 9 cases because we've got 3 possibilities here and we have 3 possibilities there as well. But also observe that this congruence only involves c and x. So we actually don't need the y part. Okay, so let's maybe look at this first case, case 1, which will be, let's take it to be c is equal to 2 and then x is equal to 9. Okay, so pushing that into the congruence, what do we have? Well, we'll have 9 times 10a plus 2 is congruent to 11a modulo 100. So that in fact gives us a linear congruence in one variable to solve. So pushing some things around, what we'll end up with is 79 times a is congruent to 82 modulo 100. Now, there are a couple of ways to determine if we have a correct solution here, or a solution that works. Let's recall that we need a to be between 0 and 9. Well, you could simply test everything between 0 and 9 and see if any of them works. Or you could find the so-called modular inverse of 79 and multiply both sides of this congruence by that, finding the value for a. This definitely has a solution because 79 is relatively prime to 100. Okay, so, well, if you were to solve this, what you would get is that a is equal to 58. But of course, That's not a real possibility. That's a solution to this equation, but since a needs to be a single digit number, that's not what we're looking for here. So I'll just put an x. That is a contradiction. There is no solution in this case when we have c is equal to 2 and x is equal to 9. So let's look at the second case. So let's say case 2, let's maybe take that one to be c is equal to 2 and x is equal to 8. So let's see, if we were to do the same kind of thing here, so push those two numbers into this congruence and move some things around, what we'll end up with is 69a is congruent to 84 modulo 100. Again, that has a solution. It's just, is that solution between 0 and 9? And it's not. If you use the standard strategies for solving this, what you'll get is that a is in fact equal to 36. So again, that's also not useful for our purposes. Now, if you work through all of the other possibilities, what you'll see is that only one of them works. And that'll be what I'll call case question mark, because you've got to work through a couple and it depends on what order you do these in. So what you'll end up with is c is equal to 4 and x is equal to 7. So let's see, pushing this into our congruence and moving some things around, what we'll end up with is 59 times a is congruent to 72 modulo 100, but then solving that, we'll get the number 8. So a is equal to 8, which is definitely allowed. That's a one-digit number. Okay, so let's see what we have here. We have c is equal to 4, we have x is equal to 7, and we have a is equal to 8. But recall, if x is equal to 7, then that means that y must be equal to 2. Okay, so looking back over here, we've determined lots of our values, our unknown values. So we might as well start replacing everything we can. Wow, now we're really in a good position. Notice that we only need one remaining digit from the quotient and one remaining digit from the divisor. And after we have that, we can definitely fill in the rest of the puzzle. In fact, we could probably fill part of it in right now, but it's not actually super advantageous to do so. So now let's focus on this digit b. And the way that we'll do that is to look at this line right here. And so notice there's an 8 in the 100s place. And where does this line come from? Well, it comes from this number 8 multiplied into b 84. Okay, so let's expand that out over here. So we have 8 times b 84 must be equal to, well, notice that it's something 8 something something. So what we know is that it's got an 8 in the hundreds place. Well, just as we did before, let's expand that out, keeping in mind that we know the digits and stuff like that, or we know what the digit b is representing. It's in the hundreds place. So note that this is the same thing as saying 8 times 100b plus 84 equals, well, it equals 1,000 times something. So I'll put a pink box for that something. Well, that's that digit right here, the leading digit, and then plus 800 plus, well, what we have left over here is, well, it's less than 100, so it's going to be equal to 10 times something plus, well, 1 times something. So I'll write that as 10 times, well, I'll use a green box for this unknown, and then plus, well, our ones place right here, so I'll use a blue box for that unknown. And now the next thing to do will be to expand out this left-hand side. So let's see, expanding out this left-hand side, we'll have 800b plus 8 times 84. But 8 times 84 is 700 or 600 and now let's take the resulting equation, which is taken from looking at these two sides, and we'll reduce this thing. Now it'll be mod 1000. So doing that, and then maybe doing a couple of arithmetic simplifications, will leave us with 8b plus 6 times 100 plus 72. So like I said, that's representing this left-hand side, is congruent to 800 plus 10 times this tens digit, plus the ones digit, which we represented by a blue box. And this is all occurring mod 1000, like I said before. Okay, so that should be 1000. Okay, but what we want to do is extract the hundreds digit of this congruence. So extracting the hundreds digit of this congruence will give us the following. So we'll have 8b plus 6 must be equal to 8. But that's not exactly true, because if we're extracting the hundreds digit and we're working mod 1000, then that means that our extraction is not an equation, but it's a congruence modulo 10. So we're left with the following congruence mod 10. But again, we can solve this. This will give us 8b is congruent to 2 mod 10. But let's see what that really means. That means we're looking for a number b, which is between 0 and 9, so that when we multiply it by 8, we have a ones digit of 2. Well, there are two possibilities there. We could have b equal to 4 or b equal to 9. Well, 8 times 4 is 32. That's a ones digit of 2. 8 times 9 is 72. That's again a ones digit of 2. But actually what we'll see is only one of these is possible. And the one that's possible is b is equal to 4. And that's because if we were to have b is equal to 9 from this line right here, which comes from taking 2 and multiplying it into, well, now 984. Notice that we have 2 times 984 is definitely bigger than 1000. Oh, but look, that should just give us a 3-digit number. But if we're bigger than 1000, we cannot be only a 3-digit number. So now, like I said before, this b is equal to 9 is not possible, leaving us with only the remaining possibility, which is b is equal to 4. Okay, so now moving on to determining our final digit z. In order to determine our final digit, we're going to just look at the entire product. So we should have this 728z times 484 equals, well, this top line. So let's transpose that over here. So we have 7,280 plus z times 484 must be equal to, well, let's transpose this top line the way we've been doing it with digits and such. So it's going to be 1,000 times something. And why am I chunking all that 1,000 together? That's because the only digit we know is the hundreds digit, so we want to use that. So it's going to be 1,000 times something plus 800 plus, well, we've got a tens digit and a ones digit. So just like we've been doing, I'll write that as 10 times some unknown. I'll put a blue box. And then plus our ones digit, which I'll write as a green box. But now since I've put all of that stuff times 1,000 together, that motivates me to look at this entire equation mod 1,000. So in other words, we're going to divide by 1,000 and keep the remainder. So what does that look like now? Well, 7280 mod 1000 is 280. So that's going to give me, and I'll flip this product, 484 times 280 plus z must be congruent to, well, we've got this 800 plus 10 times blue box plus green box mod 1000. Okay, nice. But now let's expand out this left-hand side. And doing that will give us 484 times z plus 520. And you might say, well, how's that 520? That's because I reduced mod 1000 after multiplying that 484 to 280. Okay, so now let's look at what we're really going for here. What we're really going for is some object of this form, which gives us an 8 in the hundreds digit after we reduce mod 1000. I think our best bet here is just to test all the possibilities with a chart. And so this isn't fancy or anything, it just takes a little bit of calculation. And after doing all of that calculation, you'll see that, well, there's only one of these products that you get an 8 in the hundreds digit, and that's this one right here, which corresponds to a z value of 9. But that z value of 9 gives us the only remaining digit from our puzzle, giving us a clear way to fill in the rest of the details. And there we have it. We've got our completed Feynman's long division problem. So since you like this video, I've got some other videos on some famous mathematical tricks of Richard Feynman. You should definitely check out the one on the screen. And that's a good place to stop.